Welcome to this technical deep dive on supply chain security and mobile devices. Modern smartphones go through a complex journey before reaching users. From silicon manufacturing to device provisioning and finally software updates, every step in the supply chain can become a potential attack surface. If attackers compromise even a single cryptographic key, firmware component, or hardware chip, millions of devices could be affected. That is why modern mobile security relies on roots of trust, secure provisioning, verified boot chains, and authenticated software updates. In this video, we will explore how device trust is established, how software integrity is maintained, and how secure update mechanisms protect billions of devices worldwide. To understand supply chain security, we first need to understand the threat model. Several different actors may attempt to compromise mobile devices. These include nation-state attackers, who have significant resources and aim for long-term surveillance or intelligence gathering. There are also organized cybercriminal groups seeking financial gain through data theft or device exploitation. Another major risk comes from supply chain insiders, where a compromised manufacturer or malicious employee introduces tampered components during production. Finally, counterfeiters may clone devices or steal intellectual property. Attackers can exploit multiple attack surfaces, including shipping logistics, manufacturing processes, firmware build systems, and update delivery infrastructure. If these attacks succeed, the consequences can be severe, including persistent malware, mass device compromise, data exfiltration, and long-term loss of trust in the ecosystem. Device trust begins during provisioning, which occurs at the manufacturing stage. During provisioning, the device receives critical identity information such as a unique serial number, device identifiers, and hardware unique keys. These identifiers allow every device to be securely recognized by back-end systems. Provisioning also installs the root of trust, which typically includes cryptographic keys used to verify firmware and bootloaders. Manufacturers also configure important system parameters such as debug settings, boot modes, and security policies. This process is carefully controlled and monitored, because if attackers compromise provisioning, they could permanently weaken the security of the device. Secure provisioning ensures that every device begins its life with a trusted cryptographic foundation. Mobile devices use several types of storage to protect critical security data. The most fundamental is boot ROM, which contains immutable code stored directly in silicon. This code forms the hardware root of trust and cannot be modified after manufacturing. Another option is OTA memory or fuses, which store device-specific keys that can only be programmed once. General storage technologies like flash memory or UFS storage hold operating system images and firmware updates. For higher security, devices may use a secure element, which provides tamper-resistant storage for sensitive information like payment credentials or biometric data. Some platforms also include trusted execution environments, which isolate sensitive operations from the main operating system. In enterprise systems, trusted platform modules, or TPMs, provide hardware-based cryptographic functions and secure measurements. Each of these storage mechanisms contributes to maintaining device integrity. Modern mobile security depends on several core security elements. The first is the hardware unique key, often called HUK. This key is generated directly within the device hardware and never leaves the secure boundary. It serves as the foundation for deriving other cryptographic keys. Next is the root of trust public key, which verifies the authenticity of firmware during the boot process. Another critical component is attestation keys, which allow devices to prove their integrity to remote servers. Finally, each device maintains a unique device identity, such as a serial number or device ID, which helps track and authenticate hardware across the ecosystem. Together, these elements form the cryptographic identity of the device. Secure boot is built on the concept of a chain of trust. The process begins with the boot ROM, which contains immutable code embedded directly into the hardware. This boot ROM verifies the authenticity of the next stage, which is the bootloader. The bootloader then verifies the kernel, ensuring that only trusted operating system components are executed. Finally, the operating system verifies higher-level software and system partitions. At every stage, digital signatures are checked before the next component is executed. Additional protections include anti-rollback mechanisms, which prevent attackers from installing older vulnerable firmware versions. The device may also enforce lock states, ensuring that production devices only run verified and authorized software. This entire sequence ensures that only trusted software runs on the device. To maintain software integrity, manufacturers use a secure signing infrastructure. The process begins with a controlled build pipeline, where source code is compiled into firmware images. These images are then processed through cryptographic hashing, which generates unique fingerprints for the firmware. Next, a manifest is created containing metadata such as version numbers, target devices, and rollback indexes. The firmware is then signed using secure keys stored inside hardware security modules, or HSMs. These specialized systems ensure that private keys cannot be extracted or misused. Finally, signed firmware packages are distributed to update servers. Strict key management policies, including offline root keys, dual authorization, and key rotation, ensure the long-term security of the signing infrastructure. Over-the-air updates are a critical part of maintaining device security. The process begins when a device discovers a new update from a secure update server. The device downloads the update package and validates its authenticity using digital signatures. If the verification succeeds, the update is installed in a separate system partition. This ensures the existing operating system remains intact during the update process. Before activating the update, the device performs several health checks to confirm the system is stable. Once validated, the device reboots into the new firmware. If any error occurs during installation, automatic rollback mechanisms restore the previous working version. This process ensures updates are secure, reliable, and resilient. Android and iOS use different approaches to implementing mobile security. Android is built on a modular ecosystem, where different manufacturers implement hardware and security features. Android uses technologies like verified boot, key store, and trusted execution environments to protect device integrity. Apple's iOS ecosystem follows a tightly integrated hardware and software model. Security technologies include the secure boot chain, secure enclave, and strict application sandboxing. While Android offers flexibility and customization across multiple vendors, iOS focuses on uniform security enforcement across all devices. Both ecosystems aim to protect user data while maintaining system integrity. Modern smartphones use A/B partition updates to make updates safer and more reliable. The device maintains two system partitions, known as Slot A and Slot B. One partition runs the current operating system, while the other remains inactive. When an update is available, the new firmware is installed on the inactive partition. Once installation completes, the device reboots and switches to the updated partition. If the update fails, the device automatically rolls back to the previous working partition. This approach ensures no downtime and automatic recovery from failed updates. Despite strong security designs, several operational risks remain. One common issue is weak key custody, where signing keys are poorly protected or stored on developer machines. Another risk occurs when debug interfaces remain enabled in production devices. Missing rollback protections can also allow attackers to install older vulnerable firmware versions. Additionally, unsigned factory tools may allow unauthorized system modifications. To mitigate these risks, manufacturers enforce hardware-backed key storage, permanent debug lockouts, rollback protection mechanisms, and strict authorization for factory tools. These controls significantly reduce the chances of large-scale compromise. Remote attestation allows devices to prove their integrity to external services. During attestation, a server sends a challenge to the device. The device responds with cryptographic proof generated using hardware-protected attestation keys. This proof confirms details such as the boot state, operating system version, and security configuration. Applications such as banking, enterprise authentication, and digital payments rely on this mechanism to verify device trustworthiness. Because the keys are stored in secure hardware, attackers cannot easily forge these attestations. Remote attestation therefore provides strong assurance of device integrity at scale. Rollback protection prevents attackers from installing outdated firmware. Devices maintain monotonic version counters, often stored in tamper-resistant memory such as fuses. When firmware is installed, the device checks that the version number is greater than or equal to the stored counter. If an attacker attempts to install an older version, the system rejects the firmware. Platforms such as Android implement rollback protection using rollback indexes, while Apple devices enforce strict OS version binding through secure boot policies. This ensures that once a device upgrades to a secure version, It cannot be downgraded to a vulnerable state. Securing the supply chain requires strict operational controls. Manufacturers implement background checks, role-based access controls, and dual authorization for sensitive operations. Hardware security modules ensure that firmware is always signed using protected keys. Supply chain partners must provide software bills of materials and vulnerability reports. Continuous monitoring systems track manufacturing data and detect anomalies. Factories also enforce strict physical security measures such as secure rooms, camera-free zones, and controlled access points. These measures help protect devices even before they reach customers. Let's summarize the key lessons from supply chain security in mobile devices. First, trust must begin in hardware, with immutable boot code and secure key storage. Second, systems should follow a zero-trust architecture, verifying every stage of the boot process. Third, update mechanisms must be resilient, using signed firmware and rollback protections. Fourth, manufacturing environments must be hardened to prevent supply chain tampering. Finally, organizations must prepare for failures by implementing incident response plans, key rotation strategies, and transparent communication processes. Supply chain security is not a single feature. It is a complete ecosystem of hardware, software, cryptography, and operational discipline.